should be good. Yeah, it should be good. Okay, dear participants, dear speakers, welcome to our seminar, Applied Hydrodynamic. No applied mathematics. It's a seminar on applied mathematics, but we have many presentations on hydrodynamics, on ship hydrodynamics, on what else? On ship hydrodynamics, on numerical methods, on the machine learning, on data mining, many other things. So it's not just applied mathematics. Doesn't matter how you understand it. So our speakers today, they are from New York University. There are two speakers, and Dr. Peng Zhang will start, and he will introduce himself, laboratory, second speaker, and the topic. So Peng, please continue. I will follow the. I always will be here, but I switch off my camera and my microphone. So please start.
Okay. Thank you, Dr. Galerkin, for your introduction, and thank you for inviting us to present our work. And my name is Peng. I'm from New York University, Tandon School of Engineering. I'm a postdoc there, and I work in the Dynamical Systems Lab. And today I will present the work with my collaborator, Alain Boldini. He's also working in the same lab, and both me and Alain have a research interest in mechanics, and we are both working in the same lab, Dynamical Systems Lab at NYU, with Dr. Mauricio Porfiri. And yeah, that's a little bit about ourselves. And today we're going to present a topic on the impulsive hydrodynamic loading of air-backed panels. And the presentation has two parts. The first part will focus on the experimental aspect of the problem, and I will present this part. And then the second part, we will focus on the mathematical modeling of the same problem, and Alain will present the second part. So I will start with the first part. And we did this work with a visiting student last year, Alain. And the problem that we're interested in has a background in Navy. In particular, what we are interested in is the case in which when the ship is navigating on the sea and there is an underwater explosion, and the explosion creates a water pressure wave that impacts the panel of the ship. And what we're interested in is whether this impact can cause any damage to the ship. So if you look at this case, we can simplify this as we can consider the ship as a panel that is lying at the interface of water and air, and the impact is coming from the water phase. This type of problem, we can call this an air-backed impact of the panels. It has been studied in the past by many labs, and what people normally do is they build a lab scale experiment, which is normally scaled down version of the same phenomena. For example, in this work, the authors used a plate to simulate the ship on the surface of water. So on one side of the plate, it is exposed to the air. On the other side, it is exposed to water. And they use explosive to simulate the water pressure wave that impacts the plate. And they use a pressure sensor to record the hydrodynamics of water. They use sensors to record the structural response during this interaction with water. You can actually.
Sorry, may I ask you? There is
yes.
the black rectangle. Yes, you deleted it. Thank you very much. Thank you.
Oh, okay. Yeah, I don't know how, but yeah, it disappeared. Yeah. So yeah, this type of problem, this problem has been studied in many different labs. For example, in this work by Aurora and his colleagues, they used a similar setup. They used experimental explosive charge to simulate the water pressure wave, and they placed a plate near the charge to study the interaction between the pressure wave and the plate. And again, they use a pressure sensor to measure the hydrodynamics. They use a sensor to measure the response of the plate. So in almost all of the studies, as far as we know, the measurement of the flow dynamics is mostly focused on one point. They use most studies use a single pressure sensor to quantify the flow. And what we find is that most studies, we haven't read a study that used any technique that acquired a two-dimensional measurement of the flow physics and also the structural dynamics at the same time. But we think that will be very important to understand the fluid structure interaction process of air-backed panels. So the motivation or the purpose of our study is to design an experimental method that can help us quantify the flow physics as well as the structural dynamics over a two-dimensional plane simultaneously, so that we can understand the fluid structure interaction process better. So our idea of building this experimental setup is based on traditional flow and structure measurement techniques. For the flow measurement, we used a standard technique to measure flow, PIV, particle image velocimetry. The idea, I'm pretty sure most of us are familiar with this technique. The idea is to use a laser to light up a two-dimensional plane, and we put sealing particles in the water flow. And if we can record the motion of the particles with a high-speed camera, we can actually get an idea of the flow field, the velocity field of the flow. It's pretty standard. And on the other hand, for the measurement of the structure, we use another standard technique called digital image correlation, DIC. The idea is to put speckles, random speckles on the surface of the structure. And if we can record the deformation and displacement of the speckles, we can get the displacement and strain field of the structure. So our idea is to combine these two conventional techniques so that we can obtain both the flow physics, a measurement of both the flow physics and the structural deformation at the same time. So I put a schematic of what the setup would look like. It looks simple, but there are some problems associated with experimental design. For example, we have to make sure that the two cameras used for PIV and DIC they acquire data at the same time. And also we need to find a way to deal with the light interference between the light source for PIV, which is normally a laser, and the light source for DIC, which normally is a very strong high power light source. So so the design is actually not trivial. So we tested our approach on a few problems. We started with a simple problem in which the phenomena is static. I mean, the interaction is steady. In this case, we are looking at the fluid structure interaction between a soft plate that you see in the middle in the cross flow. The flow is flowing from left to right. And the flow, the Reynolds number of the flow in this case is relatively small, so that the deformation of the structure can be considered as static, and the flow around the structure can be considered as steady. So it's a simple fluid structure interaction problem. And actually through this problem, we can quantify the uncertainty of our measurement for the flow and the structure. And we get a pretty, we can get a pretty high accuracy in both measurements. And moving on from that, we tested our experimental approach on a more complicated problem. In this case, we're looking at a plate that is on the surface of water, and there is a heavy object that falls on top of the plate. This problem is highly transient, and the interaction is happening over a very short time scale. And again, we used a similar setup to quantify the structural dynamics and the flow physics. And we were able to capture the dynamics of the structure and also the fluid loading on the structure. And we were able to understand the fluid structure interaction phenomena very well. So this shows that the approach can be applied to a study a highly transient fluid structure interaction problem. So what we want to do next is we want to apply.
Excuse me, there's a question. What's the material of the plate in your experiment?
In this experiment, the material is very soft. We use PDMS to make the plate.
What is PDMS?
It's a kind of polymer. It's the Young's modulus is around 1.5 megapascal, so it deforms very easily.
Yeah. So is this real time?
No, actually, no. It's slowed down. The whole process happens within. If you look at the video on the right, this whole process happens within 200 milliseconds.
Okay, thank you.
Yeah, no problem. Yeah, it's a scaled down version. Maybe I should have put how many times it's being slowed down. Yeah, the idea is to use the same approach to study our the problem that we proposed in the very beginning, the problem of air-backed impact. So the first step is to make an experimental design in our lab. So in the real applications, the problem, the scale of the ship is normally on the order of tens of meters, but obviously we cannot have that large of a setup in our lab. So we built a smaller scale setup. We used a flexible panel to simulate the ship, to simulate a panel of the ship. So on one side of the panel, it is exposed to the air. Another side is exposed to water. And to simulate the underwater explosion or underwater pressure wave that impacts on the panel, we used a sphere, a solid sphere that goes through the water surface. So when the sphere goes through the water surface, it creates a pressure wave, and the pressure wave will interact with the panel, and that simulates on the larger scale the case in which the ship is on the water-air interface and there is an underwater explosion that impacts the ship. So it's a scaled-down version of the real problem, and we used a pneumatic cylinder to control the motion of the solid sphere to give it a constant speed as it extrudes through the water. So yeah, so this is our experimental design to quantify the flow physics and also the dynamics of the panel. We used our combined PIV and DIC setup. We added a PIV camera to capture the flow, and we used a DIC camera to capture the dynamics of the panel. The DIC is actually capturing a bottom view of the panel. On the bottom of the panel, we put speckles so that we can record the motion of the panel. Yeah, so on top of that, we also installed a pressure sensor at the tip of the sphere so that we can get a point measurement over time, the hydrodynamic loading induced by the solid sphere. So this is our experimental design. And here I'm showing some more details of the experimental setup for both cameras. We can acquire data at 1,000 frames per second. They have a spatial resolution on the order of 1600 by 1200 pixels. And then the sensor measurement at the tip of the solid sphere can give us a acquisition rate of 10,000 hertz. And again, we used PDMS to make this panel on the bottom of the water tank. And the Young's modulus is close to 1.5 megapascal. It deforms very easily, and its mass is close to water. And if we track the motion of the sphere during the experiment over repeated tests, its motion is pretty consistent. And during the linear stage of the movement, it gives us an impact speed of roughly 0.8 meter per second. And on the right side, I'm just showing two example images of the PIV and DIC. On the top, I'm showing the PIV images with the particles around the plate. On the bottom, you can see get a view of the plate. Because of the hydrostatic pressure, the plate is deformed to some extent. On the bottom here, I'm showing the DIC image. In this circle, you can see the bottom of the plate with speckle patterns on it. Here, one thing, well, it's not a very clear view, but later I'm going to show you a zoomed view onto the speckle. Here, I want to point out that this panel is not placed exactly at the center of the image. The reason is that we did it on purpose. The reason is that we want to use the perspective of the camera to compute from the in-plane displacement, compute an out-of-plane displacement. And to do that, we need to put the panel on the side of the image and then use the perspective of the cameras. And I will use another slide to explain this in a little bit more details. So this is a schematic of how we control the hardware and how we realize the simultaneous acquisition of the data and control of the pneumatic cylinder. So when we start the experiment on the computer, we just click a button, and then a DAQ card will send a signal to the pneumatic cylinder, and the cylinder starts to extrude the sphere to go through the water. At the same time, the DAQ sends a signal to a timer box that connects the two cameras, the PIV camera and the DIC camera, and they are triggered to start the acquisition of the data. And at the same time, the DAQ will start reading data from the pressure sensor that is attached to the bottom of the sphere. So all the actuation and data acquisition were conducted simultaneously, and we repeated the experiment 6 times to give us some statistical significance. Yeah, so this is the control, and here I'm showing 2 videos of the experimental data, raw data that we acquired from the camera. On the top, I'm showing the PIV data captured by the PIV camera. You can see that the sphere extrudes and goes through the water surface and creates a pressure that interacts with the panel on the bottom. The panel, you can see some clear vibration of the panel. On the bottom is a video of the camera view of the DIC camera. It's not very obvious to you the movement of the speckles because the movement is very, very small. You can only see it is moving from maybe the shadow on the side, but it is a video that is acquired in the real time and at the same time with the PIV data. And if we do some preliminary analysis, if we use cross correlation and analyze the flow field, we can obtain the velocity field from the particle images. If we conduct also cross correlation, we can compute displacement field associated with the DIC. One thing I want to point out is that this DIC measurement, the measurement results, the analysis results I'm showing on the right, it is associated with the in-plane displacement of the speckles. But you can see from this video that the out-of-plane displacement seems more interesting to us because that is the main direction of the interaction. So later, I will show you another step that we took to convert this in-plane displacement into out-of-plane panel deflection. For the PIV velocity measurement, we can actually take another further step to convert or to infer the velocity or to infer the pressure distribution in the flow. So from the velocity field, we can integrate the Navier-Stokes equation to obtain the pressure distribution around the plate and the sphere. So I'm going to show you in more details in another slide. Yeah, here I'm showing you the two equations of Navier-Stokes equation expressed in the polar coordinates. And here, well, here the y direction is the radial direction, and z is the vertical direction. So if we consider the velocity field u and w component as known to us from PIV, and we can actually consider their gradient, spatial gradient and temporal gradients as known to us because we can compute them from the PIV. Then in these two equations, the only unknown to us is the pressure, right? If we integrate these two equations, we can get the pressure distribution. So the idea is actually very simple. And before we do that, we can actually simplify further this problem because we know that the problem has a very high Reynolds number, so we can ignore the viscous terms in these two equations. And that also helps us to get rid of some of the singularities associated with the viscous term. Of course, if we can also keep this term and use L'Hopital's rule to get rid of the singularity. And to do the pressure integration, we also need a reference point for the pressure. And the point that we use is our pressure sensor measurement at the tip of at the bottom of the sphere. So we started from that known pressure point and then integrated and obtained the pressure distribution over the entire fluid domain. So that is our analysis of the flow of physics. And for the structural deformation, I mentioned before that there is an extra step that we took to convert the in-plane displacement that is measured directly by DIC into the other plane displacement. The idea is actually very simple. We used the perspective of the camera. The idea is that when an object moves closer to the camera, the object appears bigger. So similarly, if you consider two speckles on the panel, their distance appears bigger if they move out of plane towards the camera, right? So that is just due to the perspective of the camera, and we can use that to establish a relationship between the in-plane measured displacement and the outer plane measured displacement. And their relationship can be very simple. It's a linear relationship if we assume a pinhole camera model. And if you're interested, I can show you more details later. Yeah, so the idea is I just want to point out that from the DSC measurement, we can convert our measurement into the other plane displacement, which seems more interesting to us. So after all the analysis, we can look at some of our measurement results, analysis results. So on the left here, I'm showing the dynamical temporal response of the plate, the deflection at the center of the plate over time. So over the course of around 400 milliseconds, the plate give us 4 to 5 periods of vibration. So its vibration period corresponds to less than 100 milliseconds. So actually, we can get a more accurate measurement of the vibration frequency, which is around 11 or 12 hertz. If we compare that to the vibration frequency of a membrane in vacuum, we find that in our case, the vibration frequency is much lower, and that is because of the added mass effect of water in our experiment. So that is the temporal response of the plate. If we look at the spatial response, spatial deflection of the plate, here on the right, I'm showing the shape of the deflection over half of the vibration period as the plate goes from the minimum to the highest to the maximum deflection. What we see is that the highest deflection is almost always in the center of the plate. And if we make a comparison between the shape of the deflection and the shape of a vibrating membrane, the fundamental mold shape of a vibrating membrane plotted in as black curves, we see that they actually match each other pretty well. So this means that our plate is behaving more like a vibrating membrane than a plate. The reason, I think, is because that our membrane is very soft, and the pressure exerted by the flow is high enough to deform the plate a lot, and so that the plate is behaving more like a membrane. And the stretching of the plate is high in our case. So that is the structural response, and our measurement also gives us the measurement of the flow physics. Here I'm plotting the flow velocity distribution at 3 different moments. On the left, this velocity field corresponds to the velocity when the plate is having the minimum deflection. In the center is the velocity when the plate has 0 displacement, and on the right is when the plate has the maximum deflection. And you can see that as the plate goes from the highest to the lowest point, the flow is going downwards. So their direction match each other over time. And this is the velocity distribution. And based on this, I mentioned before, we can integrate the velocity and obtain the pressure distribution in the flow. And this is what it looks like. These 3 plots of the pressure corresponds to the 3 velocity distribution that I showed on the previous slide. And from the velocity distribution, we actually found something that is interesting to us. We found that the peak pressure is not necessarily always located at the center of the plate. It is sometimes at the center of the plate, but sometimes the peak pressure is in between the clamp and the center of the plate. Sometimes it is located near the clamp. The peak pressure is located near the clamp. So the pressure distribution within the flow is not following a simple fundamental mode over time. So one major advantage of our experimental technique is that it acquires the 2-dimensionally resolved plate deflection and the flow physics at the same time. So that allows us to conduct an analysis of the flow structure, fluid structure interaction of the air-backed panels. So in order to understand the interaction, what we can do is we can just plot the two physics. We can plot the panel deflection and the velocity or pressure field, and then compare what is their relationship and what is their interaction. For example, here I'm showing the plate deflection at 5 different time instance over half of the vibration period. On the right, I'm showing the pressure distribution, actually the pressure loading on the plate computed from the PIV measurement. And it is shown at the exact same time instance. And from the pressure, you can actually see that sometimes the peak pressure is near the center, but sometimes the peak pressure is not at the center, so is not following a simple fundamental shape. If you take a closer look between the 2 parts, for example, if we pick out the maximum deflection, it corresponds to the last time instance that I'm showing here. But if you pick out the highest pressure loading, it corresponds to something, a time instant that is in between, some time earlier than this. So this means that the plate achieves the highest deflection sometimes after the pressure achieves the highest loading. So there is a delay between these two processes, and we think this is caused by the inertia of the plate. So yeah, that's it. That is all the data that I want to show. And so this study, it just shows that first of all, our experimental technique can give us data that allow us to conduct the analysis of the fluid structure interaction process. And this could be critical for the development of mathematical models, because it gives us some insight of what the physics looks like. And it can also actually help us validate any mathematical model that we develop for the problem of air-backed impact. So the mathematical modeling aspect of this phenomena is going to be presented by my collaborator, Alain Boldini. So I'm going to hand this presentation to Alain now. So I'll just stop share. Did I stop?
No, not yet.
Oh, here.
Yeah,
No.
you stopped it. Yeah.
Okay.
Thank you, Peng. Yeah.
Yep.
Can you see my screen?
Yes.
Yep.
Perfect. Thank you very much.
Yeah, please continue, Alain.
Thank you. Thank you, Peng, for the introduction and for introducing the thorough introduction on the experimental results. So as Peng said, I'm going to present the theoretical aspects of this work. And this work has just been published in Journal of Sound and Vibration. So if you're interested in more details and on the procedure, you can take a look at the paper. And it's just going to be a little bit more math-oriented, but I'm trying to keep it to keep it concise and to highlight the main passages so that it doesn't become too heavy. So the main aspect that we were interested about when studying this theoretically was the role of the pre-deformation of the membrane. And in particular, you see this is before the impact loading from the sphere. And you see that because of the hydrodynamic pressure of the water, the panel is already pre-deformed. And we thought that that was an important part in determining the fluid structure interaction. And in general, this is the pre-curvature of the structure is something that is important in many applications in fluid structure interactions. For example, in ship hulls, airplane fuselages, or air capsule pipes, heat exchangers, and so on. However, if you look at the literature, it's not very clear what is this effect of the pre-deformation. In particular, most of the studies focus on cylindrical shells because those are the ones that are more easy to treat analytically. And in addition, the previous inquiries do not consider what is the effect of the structural deformation on the fluid domain. So if you have a structural deformation, the fluid domain will change as a consequence of the structural deformation because the fluid will fill up that space. And in addition, it's not very clear what can be the analytical solutions for these problems, because most of the because of the complexity of the problem, most of these solutions that are found are purely numerical. So the objective of our study was to understand and isolate the effect of pre-deformation, and I'm going to show you how we isolate that. And in particular, we focus on the added mass effects that are that is the in-phase component of the force that the fluid exerts on the structure. And that is the most important contribution in these cases, and is, if you want, is the mass of fluid that moves with the structure, so that the mass of the structure becomes higher because of this dragging of the fluid, and therefore the resonance frequency will become lower than what we would expect from the frequency in vacuum. In particular, we want to employ a theoretical approach to obtain an expression that is semi-analytical, so like not purely numerical, of a factor that determines the added mass and is called the non-dimensional added virtual mass incremental factor, or NAVMI factor. I'm going to explain that in the next slide. And we want to understand what is the effect of the pre-deformation on this free structure interaction. So to quantify the added mass in the literature, there are some factors that have been defined so that once we know the factor, it's very easy to relate the in-vacuum frequency to the frequency of the wet structure, so the one that is in contact with water. And in particular, one of the most used one is the added virtual mass incremental factor, or AMI factor, that relates very easily, as you see, the wet frequency to the in-vacuum frequency. So the AMI factor is computed for each different mode of the structure. So in this case, it's the ith mode. And we find it by taking the ratio between the kinetic energy of the fluid that is forced by the structural motion and the kinetic energy of the structure. In particular, we use reference contributions to the kinetic energy, meaning that we scale the kinetic energy by the square of the natural pulsation of the mode. And finally, this AMI factor in reality is not independent of the geometrical and material parameters of the structure and the fluid. And therefore, we put forward a definition of a non-dimensional AMI factor, or NAVMI factor, which is the one that we're going to use from now on. And in this case, it only will depend on the configuration, so on the boundary condition, if you like. And so for a circular membrane in our case, the NAVMI factor is the AMI factor multiplied by the ratio of the densities of structures and fluid and some geometrical parameters of the membrane, in particular the thickness and the radius of the membrane. So we now put forward some hypotheses so that we can simplify the problem to find a semi-analytical solution, or to find this NAVMI. And in particular, we neglect the presence of the rigid tank and of the fluid-free surface. And this is very important. So we fix the hydrodynamic pressure, but then based on the height of the fluid column, but then we don't consider any boundary. So that helps us, first of all, to isolate what is the role of the pre-deformation on the fluid structure interaction, because we don't have the interaction of what is the height of the fluid column. And then it also helps us because since we have a semi-infinite fluid domain on top, it's more easy to find an analytical solution. And this hypothesis, though, requires that the sloshing and bulging modes of the structure are well separated in frequency, and that requires basically that the height of the fluid column and the distance from the walls is large enough. We know also, following the experiments, we focus on circular membranes so that we try to find axisymmetric solutions, and we neglect for the fluid, we neglect the compressibility effects, the flow viscosity, and the vortex shedding. So in this way, we can utilize the potential flow theory to describe the motion of the flow. And in particular, something that is very important for our purpose is that we assume that the mode shapes are not affected by the presence of water. So the mode shapes in vacuum are the same of the mode shapes in water. And this has been shown experimentally from our experiment, and it's very important because it allows us to compute the mode shapes from the in-vacuum. So what we are going to, from the in-vacuum case. So what we are going to do is, first of all, we are going to find the pre-deformation of the membrane. Then we are going to consider small vibrations around that pre-deformation so that at the point the structural problem becomes linear. And since we use a potential flow theory that is linear, we can study a linear fluid structure interaction problem around the deformed configuration, and in this linear fluid structure interaction problem, we can utilize a modal approach. So The solution procedure at this point is to evaluate from the nonlinear membrane equations the static deflection of the membrane because of the differential hydrostatic pressure. Then at that point, we evaluate the modes of the structure in vacuum, linearizing these membrane equations and considering small vibrations. Then we force the fluid dynamics problem to the structural oscillations that we find from the in-vacuum case, and we utilize this, the potential theory to find a solution for the fluid dynamics. And at this point, we also assume that we have small pre-deformations. At this point, if with small pre-deformation, we can formulate the fluid dynamics problem as a perturbative problem, from which we find a series of mixed boundary problems, mixed boundary value problems that are simpler than the original one, and so we can find easier a solution. Finally, we solve these mixed boundary value problems using the integral transforms and green functions, and we find therefore a semi-analytical solution for the Navmy factor. In particular, we focus only in this case on the fundamental frequency of the pre-deformed membrane because it's the one that we saw has the most impact on in the experiments, but it can in principle be applied to any mode. So for the structural model, we utilize a von Karman theory to describe the motion of the membrane. And in particular, we want to have a von Karman theory because it's a relatively simple theory that accounts for both the geometrical stiffness that arises from the deformation of the membrane, as well as the in-plane motion that can have an impact on the fluid structure interaction. So for these are the two governing equations, the first one for the outer plane displacement and the second one for the in-plane displacement. And you see that we have the nonlinear term for the outer plane and the hydrostatic pressure. And the in-plane stress tensor is related to a simple linear constitutive equation to the strain. And we also consider a pre-stress that accounts of, especially in the case of PDMS membranes, it accounts for some pre-stress that may be left from the manufacturing. And then we have the in-plane strain tensor that is related to the in-plane displacement and the outer plane displacement to some compatibility equations. With respect to the boundary conditions, we assume that the edge is fixed as we had in the experiments, so that the displacement, the outer plane displacement is 0 and the in-plane displacement is 0 as well. To find a solution for the static deflection and structural vibration problems, we utilize a Galerkin approach. So this means that we project our equations on a series of shape functions and we formulate our model as in terms of generalized coordinates for both the outer plane and the in-plane displacement. Typically, we utilize the same number of shape functions, and we saw with a convergence analysis that even utilizing a single shape functions is enough to capture the structural deformation. And for these shape functions in particular, what we utilized were the axisymmetric modes of the undeformed membrane. And these are expressed simply as in terms of the Bessel function of zero order and its derivative. So we can at this point consider the static problem from for the membrane. We can find a weak formulation, apply Gauss theorem, and substitute our solution for the our shape functions. And what we find in the end is simply a nonlinear algebraic system for this term zeta 0, which is the generalized coordinate for W. We don't have the generalized coordinate for U because the two are related in the static problem. And it's a bit complex. It's not the prettiest equation, but it's simply a nonlinear system that we can solve easily numerically, evaluate numerically. Then we find from this point on, we consider the modal analysis in vacuum. So we found the static deflection, and we consider a small a small displacement with respect to that static deflection. And at this point, we linearize the equation of motion around this static deformation. And again, we utilize the Galerkin approach with the same-state functions because the boundary condition did not change. And in this case, we will have these generalized coefficients. And we obtain this generalized eigenvalue problem with the natural possession of the modes, the mass matrix, and the stiffness matrix that have the components for the in-plane and out-of-plane motion. And we solve this generalized eigenvalue problem, and what we find is, first of all, the fundamental frequency of the fundamental mode, and we can also find the mode shapes in vacuum that we will utilize as forcing boundary conditions for the fluid dynamics problem. In addition, we also find the first term of the Nabby factor, which is the reference kinetic energy of the membrane that is found from integration of the fundamental mode shape in vacuum. So at this point, we move to the fluid dynamics problem. As I said, we utilize the potential theory. So the Laplacian of the flow potential must be equal to 0. And this is the expression of the Laplacian in axisymmetric coordinates. As boundary conditions, we have that the velocity normal to the fixed wall must be equal to 0. So if we are not on the membrane. And then we are going to have that the normal velocity to the membrane, so the normal velocity of the fluid in contact with the membrane must be equal to the normal velocity of the membrane, while at infinity, or the potential and its gradient must be equal to 0. At this point, we utilize again a modal expansion for this fluid dynamics problem, and in particular, we consider the harmonic function in the modal expansion of the structural deformation, such that ultimately we are going. This is going to cancel out, and we are going to consider only the spatial variation of the fluid potential. And this is different for every mode, but we are considering only the fundamental mode. So instead of phi0, I'm just gonna drop out the 0. And we found the governing equations and the boundary conditions that are from the previous equations. And in this case, we see that at this point we can insert the mode shapes of that we found in the previous problem for as a forcing condition of the potential near the membrane. At this point, we have an irregular domain in the coordinates r and z because of the deformation of the membrane. So what we do is to map this irregular domain into a regular domain that is just the one that we would consider for in the case of a flat membrane, to this direct mapping that consider both the z coordinates and the shape of the membrane of the wall. So this eta goes from 0 to infinity now. And at this point, we pay the price of having a regular domain by complicating the governing equations. Before we had a very simple governing equation and boundary conditions. Now the governing equation and the boundary conditions are much more complex. So at this point, what we do is to limit ourselves to small pre-deformations. So we introduce this parameter epsilon, which is just the deflection at the center of our membrane. And this parameter is chosen such that the problem is analytically solvable for epsilon equal to 0, which is the case of the flat membrane for which the solution is very well known. And then we expand our variables in a power series of these parameters. So at this point, we substitute this power expansion in the equations, and we group the terms with the same order of epsilon, and then we let epsilon goes to 0, and we obtain at this point for each order of epsilon a series of mixed boundary value problems that are easier to solve than the original problem. In particular, so this is just a very brief sketch of the solution. For the zeroth order solution, this is just the case of a flat membrane, so we can solve it analytically with the Hankel transformation. And this is the solution. And then for the first order solution, instead, is a little bit more complex because we have the forcing on both the boundary condition and the differential equation. However, the problem is linear, so we can decompose it into a problem with the Laplace equation that, however, solves the non-homogeneous boundary condition, and instead the solution of a Poisson equation, which is our second problem, with homogeneous boundary conditions. So at this point, we solve the Laplace problem is the same as the zeroth order solution, but the boundary condition is a little bit more complex. So it's we cannot solve directly with an analytical solution. We need to do some numerical integration in this case. And for the Poisson problem, instead we utilize the method of the green functions. At this point, we found the potential. And once we found the potential, we are ready to evaluate the NRB factor. And we can find from integration the kinetic energy of the flow. And that in this case, we conduct to the case to an integral over the boundary of the membrane by using Green's theorem. And then we already found from before, from the structural problem, the contribution of the kinetic energy of the structure. We take the ratio and we find the NRB factor. So we did this with this procedure, but we also validate our results using finite element simulations, and we obtain a very good agreement between the two. So first of all, as a first result, we looked at the dependence on the membrane parameters to see if we were able to measure the experiments. And in particular, for the experiments with the PDMS membrane, we found that the deformation, the static deflection was about 15 millimeters, and the fluid, the frequency in contact with the fluid was 15 Hertz. And by varying a little bit the material parameters, considering that it's a polymer, we found that we can actually match these experimental results. In addition, we see that for the static deflection does not depend very much on the pre-stress that we have in the membrane, but is more dependent on the Young modulus. Whereas it's exactly the opposite for the frequency in vacuum, where we have a much higher dependence on the pre-stress than on the Young modulus. But we see that it's also not interesting, is not symmetrical around 0. Then we also find the dependence of the NRB factor on these parameters, and you see that similar to the static deflection, the NRB factor depends mostly on the Young modulus. So it means that there is a much more important component of the static deflection rather than the frequency in vacuum in determining the NRB factor. So the wet frequency is a mix between the two, meaning that we still see a large dependence on the pre-stress, because the original in vacuum frequency depends very much on this pre-stress, but also we see a dependence now on the Young modulus because of the dependence of the NRB factor on the Young modulus. So at this point, we fixed our parameters, and we looked instead at what happens if we change the pre-deformation. So this is the NRB factor, and we see that the NRB factor increases with an increase of the pre-deformation. And with respect to the frequency, this means that if we consider the in-vacuum frequency, which is the blue one, and the red frequency, the wet frequency, which is the red one, you see that the differences between the two increases as we increase the pre-deformation, so that the slopes, as you see, are very different. In addition, we looked at the flow physics, and in particular, we connected this increase in the added mass to the fluid potential, and we found that the fluid potential close to the center of the membrane becomes much larger in the case of large pre-deformations. And in fact, you see that this is with the same scale, you see that the potential here is much smaller than the one that we obtain here in this case. And this is also mirrored by an increase in the pressure toward the center of the membrane. So we can find the pressure from Euler equation for the fluid. And we are plotting now just a non-dimensional pressure. And you see that going from the small pre-deformations, which are here at the bottom, increasing the pre-deformation, increases the pressure toward the center of the membrane, but also along the membrane. In conclusion, what we did was to study the vibration of this air-backed circular membrane with the pre-deformations that we try to isolate what is this effect. And we modeled this free structure interaction problem using von Karman theory from the membrane and potential theory for the flow. And we utilized potential theory to find the analytical expression for the added mass effect. And in particular, we found that, as we expected from the experiments, the presence of this pre-deformation is radically changing the fluid flow. So in particular, our results show that there was a significant increase of the added mass effects when we consider larger pre-deformations. So our future work will focus also on extending this model to account for some phenomena that we did not consider in this first study. In particular, we can look at larger pre-deformations that are not considered in our case where we use a perturbation analysis. In case of marine applications, we can look at non-isotopic composite materials, in particular to orthotopic composites that are now the standard. And it would be interesting also to study what is the interaction between the pre-deformation and the free surface effects that we have now neglected. And something else that it's important to consider when considering shock waves and blast waves is the compressibility of the fluid. So with this, I would like to thank our sponsor, the Office of Naval Research, for funding our research. And we would like to thank you for your attention. And if you have any questions for me or Peng, we will be happy to respond.
Thank you very much. Thank you, Alain. Thank you, Peng. We have not enough time for questions. I mean, formally, because our seminar for 1 hour and we have 1 hour left, but potentially we can stay longer. Okay, not with all our participants, but with some of them. And if any questions, you can unmute your microphone and to ask Peng or Alain, depending what your question is. Karima, do you have a question?
Just a quick question. If possible, I'm curious, usually polymers, from my experience, display rather strong viscoelastic properties. Why this did not matter in your experiment? I mean, viscoelasticity.
Yeah, so yes, I agree with that. The polymer that we use is more like a rubber. So they do give us a plastic deformation. For example, if we leave water in the tank on top of the panel for a very long time, we do observe some kind of a permanent deformation of the panel. Yeah, we do observe that. But based on what we see from our experiment, after we do experiment, they do go back to their original shape, at least during the process of doing the experiment. So during the experiment, I would consider them as plastic. I mean, as elastic, but over long term, maybe, yeah, you're right. They become a plastic and give us plastic deformations.
You misheard me. I did not mean plastic. I meant viscoelastic. So that's exactly the behavior that you are describing, right? So there is a temporary residual deformation, but there is no permanent residual deformation. That's viscoelasticity rather than plasticity. Yeah, and I would think that this should influence, so it should be some effect in polymers.
Yeah, maybe. Yeah, I agree.
Basically, attenuation of the signal and so damping mostly, I think, but also there could be some other effects related to that property.
Yeah.
I agree. Thank you.
Thank you.
Thank you for your comments.
Can I add some comments for these questions?
Yes,
in our experience, that is usually if we have a very short event of very short duration, we never have viscosity, we have only elasticity, and it is absolutely different behavior for example, the elastic plate on the wave and for elastic plate for the very strong impact or very strong exit or something that is also we have some problem if we calculate that a strong vibration of the plate that is was absolutely different behavior, that is not expected behavior. Every time where we have an event of very short duration, we obtain something very specific, and maybe
I see.
if you compare results with the floating plate, with the wave on the floating plate, and the case with impact is absolutely maybe different behavior.
I assume Tanya is making reference to our paper, which just accepted and should be appear soon in Physics of Fluids. Its impact on floating viscoelastic plate. That is related to ice, floating ice, and impact on it. But in your case, it's impact from the liquid, say from below, but in our case, impact from air on it. But still, it's interesting. And what Tanya is saying, indeed, the viscosity always we think, not always, but we think that viscosity or viscous properties of material are important for a large duration or for high frequency. But it's interesting that the viscosity increase what we observe the loads and making the structure in some sense more rigid than it is. Just because the viscosity, because the viscosity is kind of the memory effect, and it's for short duration. If you look just at the equation, you can find that there is effect. It's not in case Young model. No, it's another. It's a short duration. Interesting what the Karima and Tanya noticed in the for the experiment and for the modeling. Yeah, and I noticed that in experiments you have no impact actually. So the sphere approach the membrane, but do not touch it. Doesn't touch it. So the why you did that?
So yeah, we're trying to approximate the underwater explosion as much as we can. So the underwater explosion, if you think about this, is a water wave, a pressure wave that impacts the panel, rather than a direct contact between an impactor and the panel. That is why we avoided the impact, but just generated the water pressure wave using the solid sphere, and then the pressure wave impacts the panel, and then we study the interaction. Of course, it's still different from the real case, but I think this is some kind of a better approximation to the real case than impact case.
Yeah. But it's good. It's good for theory. It's good for Alain in some sense, because if there would be impact, it would be impossible to model it. I mean, through water. So that is a kind of known theoretical difficulty. So the two surfaces cannot impact each other theoretically through water. So then you need to use takes to arrive at nice solution. But in your experiment, you just avoided that. And as I understand, in the theory there are no impact at all. So in theory, you just investigate the dry and wet modes and their relations, right? So it's more about kind of the eigenvalue problem. Oh, yeah, natural vibration. Yeah.
Yeah, that's correct. Because in the end, one in the end, one can consider the impact as a Dirac delta, if you like, and then we can consider the individual response of each mode at that point.
Yeah, yeah, and you can use your mode, your analysis, kind of to combine finally them all together and to find that principal coordinates of the modes to simulate what's happening in the experiment. Okay, okay. The question in your in your modeling, in your theory, the elastic membrane, not elastic, complicated membrane, but still membrane, it's built in a flat plate. Right? Yeah, so there are no free surface, and you mentioned that there are no free surface. This is approximation. It's okay, but that approximation, there is difficulties with that approximation, because once you calculate wet modes, you need to satisfy the conditions that theoretically that normal integral of normal derivative is equal to 0 everywhere. Normal derivative of the potential. That is the solvability condition, right? So it comes from the incompressibility of the liquid, right? So, if there is a free surface, then another mode which doesn't satisfy this condition may appear, right? But I'm not talking about the compressibility, because that is the separate story. Yeah. Any other questions? I'm talking too much.
That is, I just said that is again, that is another reference for our recent work.
Yeah. We are just working on that.
For the second part of the presentation.
Yeah, relation.
Just in April was the International Workshop of Water Wave and Floating Bodies, and we present that comparison wetted and dry mode, the frequencies of wetted and dry mode, a bit different case, but also was a very analytical research.
Yeah. But Alain, may I ask you, please, to send me references or references?
This was my second question.
Sorry, Tanya, sorry. About the non-dimensional edit mass factor.
The dimensionless or dimensional?
Non-dimensional. NAVMI.
Yes, I will share with you.
Yeah, because we are kind of doing the same things, but we are not saying that word. So it would be right to make reference to that stories. And if you did already something in that field, just also send please by email reference about that, just to speak in modern scientific language. Not in old-fashioned like edit masses, which could be more than 100 years old. Yeah, and about the experiments, I have a question. So, Peng, you was talking about the viscosity during effect of viscosity, and it seems that this not so much, not really much the explosion, because the explosion is still a very short process, and viscosity of liquid could be not so important. But you potentially, I think you could have in mind another or other applications when it's happening, when something approach elastic wall or elastic panel with in regime you studied. So the more or less small velocity, small approach. It's like could be fish, could be something else when the viscosity is indeed extremely important.
Yeah, I agree. Yeah, especially if you are getting close to the panel and then you reach the boundary layer of the panel, then viscosity should be considered as important. Yeah. I agree.
Yeah. But it's very complicated problem, and it's also on our list. If the elastic plate and the liquid elastic plate with the liquid on one side, and the body approach this elastic plate, because once it's approached, the pressure in that gap becomes very large, and the velocity are very large. So it's not clear, is it a boundary layer, viscous boundary layer, or something else? But it's likely that it's a so-called thin layer approximation over there. Likely the viscosity is important, but it's also the inertia is important.
Right.
And that is very complicated problem to study. And if it would be possible to do that, not only by theoretical means, but by experiments, by PIV, by other techniques, visualizing what's happening in this, very narrow gap with large velocity. This would be very good work, I think. Yeah.
Yeah, that's very interesting.
Very interesting. Yeah, indeed. Yeah. Yeah. And yeah. Yeah, it's also, Alain, it's interesting how you solve the Poisson problem. I mean, after the perturbations, you said you use gain functions. So this means that you integrated you calculated three-dimensional integral, or two-dimensional because it's axisymmetric. You calculate.
Yeah, that's correct.
Yeah, but yeah. But
we limit integration to close to the plate, where we see that there is an effect that we did a convergence analysis on how much we need to integrate to obtain a consistent.
Okay, yeah. We did something, not like this, but with perturbation of the boundary. But it seems that, if you make that perturbation, but we did no, it was three-dimensional. Our problem was the plate, rigid plate on water surface. But the plate is of complicated shape, right? And we need to find edit mathematics, but it's rigid plate, right? And the effect of the geometry of this plate on the edit mass. And then we use the transformation such that after the transformation, the plate go to the circular cylinder, or circular disk, but the Laplace equation will be very complicated, and like what you did, yeah. But then we manage to find at each step. It's possible to find such formulas that at each step you need to solve Laplace equation, not Poisson equation. So this is it's come from the if you formulate the original problem and make that perturbation as you did with your shape. I believe it could be similar story, and then you kind of expand or use the perturbation theory for your original potential. And then you can find that the original potential is made of many terms. And the lower terms give contribution to the higher terms through the derivatives, right? But then if you formulate problem as you did, then you can find and at each step that if you use that expansion of your potential, each term in that with the derivative, then they are solved, or they are particular solutions of the Poisson equation.
Okay.
Yeah. So it's we didn't publish it, and it's interesting technique because the Poisson equation is complicated, and even it's axisymmetric. It's two-dimensional integral, and each time step many times. It's quite heavy to calculate, but potentially possible to reduce it to the Laplace equation if you find. Occasionally, if you find the particular solution of that which satisfies the right-hand side of that equation, So it could be easier just to go straight, with the computation. Sometimes, it's a kind of more kind of efficient to do that, or at least it's quicker than to do that. Yeah. Any other questions? Any other questions? Yeah. So then it seems that almost everything. Thank you very much. Very interesting to know what you are doing, how you are doing. I'm happy to see that you are checking everything carefully, going through that, even the convergence. So that is very, very, very good. Thank you very much for your
Dr.
patience, and
thank you. Thank you.
Yeah. So they are working with Tanya, and that part about the relation between the wet and dry modes is actually we did everything, but we couldn't find time to write a paper on it. But we did presentation, so we have some results, something published, but not so much. So that is very good to have this interesting and helpful seminar today. Thank you very much.
Thank you for inviting us.
Some partial problem.
Thank you for hosting us. Thank you very much.
Yeah. So then I close the this seminar. So I will write Peng and Alain to both of you, asking your permission, if you give me permission, to upload this to public use. But that should be done formally, right? And so far, I stop recording.